Okay, let me start. So let's recollect the basic definitions we had. We introduced were those of convergence and completeness. So I have a metric space. Then we have first, if you have a sequence xn belonging to x and x not belonging to x, we say xn converges to x if for every epsilon positive there exists a stage beyond which everything is close enough to x naught within distance. And we also observed that if a sequence converges in a metric space converges, the limit is unique. Two different points. And the third important point we had was that we defined xn belonging to x is said to be a Cauchy sequence is a very important notion, the notion of Cauchy sequence. If again for every epsilon positive there exists a stage beyond which all the members of the sequence are within epsilon distance of each other. At a certain stage, all the members of the sequence are within epsilon distance, and that epsilon distance you can make as small as you want, then we will find a stage beyond which that happens. Then it is said to be a Cauchy sequence. Then we found that if xn converges, then it must be a Cauchy sequence. On the contrary, in the real line, if there is a Cauchy sequence, it must also converge, the reverse. However, in general metric spaces, this is not true. Okay. So, whereas in the standard metric space R with the unit metric, every Cauchy sequence converges this is not true in a general metric space. These properties are called complete metric spaces. So, we had this definition: if x rho is such that every Cauchy sequence converges, then it is called a complete metric space. Otherwise incomplete, otherwise and called, it is called an incomplete metric space. Okay. So those are the aspects we discussed last time, just the summary of what we did last time. So what I will do is, first of all I will look at some examples of some of, and vis-a-vis the standard examples of metric spaces that we have already seen, and then subsequently try to explain why this notion of completeness is a very important notion in analysis. Okay. It's obviously an important notion because it says such a for limiting processes, quite adequate to carry out limiting processes. Okay, so let's look at some simple examples. Our first example is of course the real line with the usual metric factor for all the first the complete metric space. So what we will do now further, R1 to R2, R3, R4, etc. So in general we will take Rn, n component vectors instead of just one component, and then once we go to n component vectors, we have various possible metrics, the rho p matrix. So we look at in the context of each one of these metrics, how does Rn behave. So let us look at let 1 less than equal to p less than infinity and consider the metric space L P, did I put n? N components all are real. So what does that mean? I am considering vectors with n components, all components are real, the metric is the metric. So if x is equal to x1, x2, xn, y equal to y1, y2, yn are two vectors in this space, we define, we have rho p of xy is just summation j equal to 1 to n mod xj minus yj to the power of p to the power of 1 over p. That is our definition of this metric space. We take n component vectors, the distance between two n component vectors, for each p we get one metric space, p equal to 1, p equal to 1.1, p equal to 47, any p greater than 1 we get one metric and we get a metric space. So first of all we shall look at what does convergence really mean in this space. Exactly do we convert space? So let us take xn in this space and x in this space. So we say xn, I will use the short symbol, xn converts x in this space. So we would like to see exactly this boils to, okay, in simple terms. So now let us let me slightly change this notation. Each one is made up of n components. I need two indices, so I will use the sequence indexing as the superscript. Okay, indexing is the superscript and component indexing is the subscript. So we have, for example, x1 is the vector x11, x12, x1k, etc., x1n. And then similarly x2, I will deliberately write this now, x2 is this, x2k and x2n. And so in general, the nth one is going to be equal to, its first component is xn1, xn2, xnk, xnn. Like an infinite number of people are there. For each person, I note his weight, height, blood pressure, sugar, qualification, whatever it is, salary. So parameters that I am okay. Now what I will do is, suppose I look at the age alone of all these numbers. That means I am going to look at the first, then look at the second coordinates alone, third coordinates alone. So instead of looking at the whole thing, let us say I put some filter component for each one of them. So therefore I will get a sequence of first components. Similarly, sequence of components, sequence of nth component. So from this sequence, I n different sequences. Now each one of the new sequence is simply a sequence of real numbers. If I take only this column, it is a sequence of real numbers. This is a sequence of real numbers. This is a sequence of real numbers. So basically, therefore, when I say a sequence in this space, what I mean is an infinite matrix. The number of rows is infinite, but the number of columns is capital N. And now I am going to look at column, and that may have some as a sequence in real numbers convergence, and this whole matrix viewed as a sequence that may have meaning in convergence. What is the relationship between them? So first of all, what is given to us? Suppose xn converges to x. In LPN. So I am looking at metric space convergence. How is it related to coordinate convergence? Therefore, we look at this. First of all, what does this mean? We have the definition. So given for any epsilon positive, there exists a positive integer n epsilon such that n greater than or equal to n epsilon implies rho p xn x is less than epsilon. That is the definition to x. We have an expanded clear version of what rho p means. So if we use that, that is n greater than or equal to implies summation j equal to 1 to n mod xn j minus xj to the power of p to the power of 1 over p is less than epsilon. That is what the definition says. The definition that xn converges to x says this: given any error, there is a stage beyond which the total error is less than epsilon. See, this measures basically the error between the component of the nth member and the jth component limit, and now we are going to put all the components together and take some kind of quantification of the error, and that error I can make less than epsilon. So it's some way a consolidated error. Now, what does this consolidated error reflect in terms of individual component errors? That's what we are going to look at. So this is what is given to us, this whole thing. When I say xn converges to x in this metric space, what precisely is given to us is that fact that for any epsilon, that is for any error beyond a certain stage, that consolidated error can be made less than epsilon. Is that okay? Now, any one of these components. So, take any fixed k, take any fixed k, of course, one of the where k is 1 and n. So, take any one of the components, it does not matter, take any one component and look at the component sequences. Then xkn, if you look at kth component for all these vectors n equal to 1, 2, etc. So, I will get x1 1 k which is a real number, xk which is a real number, x3k which is a real number and so on. So, we get a sequence of real number is a sequence of real numbers. That is the first thing that I observe. If I now look at this sequence, that is a sequence of real numbers. That is like I am focusing on, say, the salary of the person, the first person, the second person, the third person, the fourth person and so on. So, I am fixing one item and I am looking at the value of all these items for every one of the members of that original sequence. Now, if you look at xk n minus xk, that is the same as okay. Let me even do this first. Look at to the power of p, xkn minus xk to the power of p. This is basically without this one of the terms here. Here I am taking all the components, there I am taking only one of the components. So, that is going to be less than or equal to, if I put all the errors together, that xjn minus xj to the power of p, right. Now, take the pth root on both sides. If I take the pth root, I will just get this. Here I will get summation j equal to 1 to n mod xjn minus xj to the power of p to the power of 1 over p, right. But now, from here, for all n greater than or equal to n epsilon, that is less than epsilon. So, this is less than epsilon for all n greater than or equal to n epsilon by 1. I am writing these proofs in detail because these are the basic things. Afterwards, I will not, may not be proving many things. All you have to do is show that you know what to do. Okay, right. So, now what does this say? This is a sequence of real numbers such that beyond a certain stage, the difference between them and xk becomes small. Therefore, this sequence of real numbers converges to this number xk. Okay. Hence, the sequence of real numbers xk xnk converges to xk for every k equal to 1 to n. This is a sequence indexed by this index, sequence indexing is n. Right. So, what we have got is, if we have convergence in the metric space, then every one of these columns converge to the corresponding coordinate of the. If xn converges to x, the first column will convert to the first coordinate of this, the second column will convert to the second, this and so on. All this coordinate wise convergence. Okay. So that is we have coordinate wise convergence or component wise convergence, whichever we want, coordinate wise convergence. So the conclusion is xn tends to x in LPNR means xn converges to x coordinate wise. Remember, we talk about point wise convergence. This is also point wise convergence. It's defined and each one of these points the values are converging. That's all. Okay. This is exactly what is the notion of point wise convergence. So whenever we have convergence in this metric space, we automatically have netwise convergence. I mean, some of the generalizations is what you do in stochastic processes and all, but basic idea is this. Okay. Now, what about the reverse? Suppose I had coordinate wise convergence, will I get convergence in that general sense of the metric space? In other words, I am able to control individual errors. Can I control the consolidated error? Obviously I can, because there are only finite number of errors, so I can make each one of them less than epsilon by n, so the total will be less than epsilon. So I will write it simply that it's easy to see that. This is what this means, that I am lazy to write that, you should go and fill it up. Okay. So it is easy to see that coordinate wise convergence implies xn converges to x in LPR. So all this fuss about metric space convergence space is nothing but just each coordinate separately and look at them. So lucky thing is, if you have n students, you allot each coordinate to one student and ask him to go and check it. Now you know from the reports from each one of the students that there is convergence or not. Okay. So therefore this is B. So A and B imply the following major conclusion: convergence in LPNR for 1 less than, first I will write this, so far seen is equivalent to coordinate wise convergence. This is the main conclusion. Convergence in these metric spaces is synonymous with looking at, so in other words, that whole matrix looks very messy. Just look at each one of those infinite columns, analyze them. If you got the convergence, you have got the convergence, and the limit will be having coordinates which are the limits of these column sequences. Okay. So that's this is what eventually what is called as the finite dimensional fiasco. We had a lot of nice finite metrics to give the same idea of convergence. No new idea. If it convergence in this, if you converge in p equal to 14, it means point-wise convergence. If it converges in p equal to 18, it means point-wise convergence. Which means convergence in any one of the metrics, this is the advantage that we get. Convergence in any one of the metrics means convergence in all other metrics, because they are all the same as coordinate wise convergence. Therefore, when we are doing estimates in a general problem, we will do estimate in the which is convenient, whichever metric is convenient, we will use that and thereby conclude that you can choose any metric, you will get the same convergence. So basically, therefore, the main thing is, okay, convergence of a sequence of vectors in Rn in any of the metrics, in any one of the metrics, rho p implies convergence in all metrics, convergence in all rho p metrics. Can you speak a little louder, please? We will come to that. We will go step by step. Okay. Right now, I have been putting this n. That is our first set of examples. Then we will go to the next set of examples and see what happens. Okay. At the moment, we are at the first level of examples. We will definitely look at that within a short while from now. Now, this is exercise. See that this is also true if we take p equal to infinity. What is the p equal to infinity norm? The metric maximum. Even in that, if the maximum difference itself converges, of course every individual will converge. So basically that is not a very big, in fact this estimate becomes, this is less than or equal to the maximum, and the same thing goes through. Maximum, yeah, therefore this has to be replied by maximum of xjn minus xj, and you are done. So therefore, for all p 1 less than or equal to p less than or equal to infinity, if it converges in one metric to x, it will converge to x in all the other p metrics. And if it fails to converge in one, don't waste your time with any other p metric, it is not going to converge in any other p metric. Okay. So sometimes it is convenient to use the infinite metric, sometimes it is convenient to use the L2 metric, sometimes it is convenient to use L1 metric. So whichever is convenient we will use to check the convergence. We will see little more on this. There are many more metrics which are also going to mean the same. Okay. In fact, every normable metric, this will be the same. But we are not yet introduced the notion of norm. So at the moment we will know only these p metrics. Okay. The next question is, along the same lines, we can see that if xn is a Cauchy sequence, then the coordinate sequences will also be Cauchy sequence. Same estimate except xn minus x there, I should write xnj minus xmj. So analogously, we see that xn is a Cauchy sequence in LPNR if and only if it is coordinate wise Cauchy. What is my coordinate wise? The coordinate sequences form a Cauchy sequence. So convergence means coordinate wise convergence, Cauchy means coordinate wise Cauchy. This will help us. These two ideas are going to help us now to determine the following question. Now, question is LPNR complete? To decide whether something is complete or not, as far as we know only a definition of completeness. The definition of completeness says something is complete if and only if every Cauchy sequence converges. So therefore, in order to establish that this is a complete space, we have to take an arbitrary Cauchy sequence in that and conclude I will find a limit and he is the limit, therefore he converges. So, to establish LPNR is complete, we have to show that for any Cauchy sequence xn in LPNR, there exists an x in LPNR such that xn converges to x in LP. This is what we have to show. We have to show that if you take any arbitrary Cauchy sequence, I have a limit. Therefore, every Cauchy sequence converges. I have to establish this convergence. Okay. Now this is you are giving some arbitrary Cauchy sequence. I don't even know the limit. That LP space is so big. I have to go and search for the fellow somebody there and check whether he is the limit. If I have to go on checking everybody, are you the limit, are you the limit, are you the limit, there is no limit to it because there are an infinite number of them. So therefore, we have to have some strategy. What is the strategy? The strategy is, first of all, there is a murder, therefore there must be a murderer. So you don't know whether there is a murder, somebody says that this is a murder, go and find the murderer. So first thing is, you have to nail down the possible candidate or possible candidates, collect evidence, and then finally establish in the court of law that he is indeed the murderer. So here, analogously, we don't know who is that fellow X. So we are going to find most reasonable guess for this X and then say he is only a guess, but now I will establish that he is the real limit. Whenever I do this, I always remember once I was attending a lecture in the ICTP in Trieste, Italy. There was one professor from Cambridge, a very famous fluid mechanics man. If there are anybody here, any fluid mechanics, mechanical engineers, Brooke Benjamin from Cambridge. He had a very beautiful style of lecturing. He would always say that I will prove to you beyond all reasonable doubts that this is true. 3 or 4 times I kept quiet, and the 4th time I said, sir, you have to prove. There is no question of a reasonable doubt and an unreasonable doubt. A doubt is a doubt. So you may prove in a court of law beyond all reasonable doubts, but in mathematics you have to prove, period. Okay. So therefore nothing like there is a fellow, if I am sleeping in the class, I won't even have a doubt. That doesn't mean you have proved beyond all reasonable doubts. All the fellows sitting there were unreasonable. Okay. So therefore, we have to actually find a candidate and mathematically establish that he is indeed the limit. Okay. So now we are given the sequence is Cauchy. Therefore, immediately we know that the coordinate sequences are Cauchy. But now the coordinate sequences are Cauchy sequences of real numbers. And we observed that in real numbers, every Cauchy sequence converges. And therefore, the coordinate sequences will converge. But the moment the coordinate sequences converge, we have equivalence, the sequence will converge in the metric. So that is what beyond all doubts, beyond not only reasonable but even unreasonable doubts. Okay. So Xn Cauchy in LPNR implies Xnk Cauchy sequence of real numbers for every k, 1 less than equal to k less than equal to n. Why is this? Because of this. Where is that? Wherever I wrote. Analogously, the Cauchy sequence, if and only if it's a coordinate wise Cauchy sequence, which implies every Cauchy sequence of real numbers converge, implies there exists an xk belonging to R such that xkn converges to xk for in R for every k. Okay, because xkn is a Cauchy sequence, this column is a Cauchy sequence of real numbers, kth column. Any Cauchy sequence of real numbers will converge. So the kth column is going to converge. Call the limit as xk. Now we have the limit of the first column, which is x1, limit of the second columns, which is x2, and so on. So I have got n real numbers. I am going to form a vector out of it. Okay, implies, so let x equal to x1, x2, xk, xn. Okay, clearly x belongs to Rn, it is an n component vector, and xn converges to x coordinate wise. Okay, because the first component converges to x1, second component converges to x2. But then if they converge coordinate wise, they will have to converge in LPM, so which implies xn converges to x in LP and R, because we have just now established that convergence in LP and R is the same as coordinate wise convergence. Okay. And therefore, every Cauchy sequence has a limit, and hence the space is complete. Okay. So therefore, that implies thus, therefore every CS, I will write Cauchy sequence in LP and R converges. Therefore, LP and R is a complete metric space. Okay. All these spaces are complete metric spaces. Okay. So basically, therefore, what it all boils down to is, in these spaces, essentially all we have is only one notion of convergence. You just do it for every component. The n component vectors, the Rn is made up of n components. So do the convergence n times, one for each component, and you get the notion of convergence for Rn. Okay. So basically, therefore, it is Rn is R made up of n times, and that convergence is also made up of n such convergences. And even if one of the pieces fails to converge, consolidated, it is bad. Individually, many coordinates it may be okay. Suppose I had 100 components, 99 components converged, and one of them didn't, then the whole thing consolidated does not converge in LP. Okay. So therefore, we have got one whole class of complete metric spaces, LP and R. Okay, if you take n equal to 1, you get the real line with the usual metric. For n equal to 2 onwards, we get many 2-dimensional, 3-dimensional, all those spaces, which are all nice complete metric spaces. Okay, now somebody raised the question. So it is therefore natural for us to look at, when we go to not a finite number of components, but a sequence of components. Then what will happen? I will have a sequence of components and then a sequence of elements. Now that my matrix becomes completely infinite number of rows and infinite number of columns. So I will have to handle it. Whenever you are dealing with infinity, there are a few things which are likely to create problems. And that problems we have already taken care of. So therefore, the next set of examples will be, let us take again LPR. What does that mean? We are going to look at all sequences such that we are going to look at only those sequences for which this mod xj to the power of p is finite, right? That is what this LP and R is here. Such restriction was not needed when we are dealing with finite number of components, because they were anyway finite. There are only finite number of them. Whenever you have infinite series, there is a divergence possibility. So remove all those fellows who are infinite summation. You take only those fellows for which the sum of the components is finite. The peak power. Okay, this is what is meant by LPR, with the distance defined as summation j equal to 1 to infinity mod xj minus yj to the power of p to the power of 1 over 2. This is our space. Now, from finite to infinite components, we have moved a sequence of components. So again, we ask what is meant by convergence in this space. Same questions that we did now before for LP NR, we are going to ask. So what is meant by convergence? So Xn belongs to LPR. X belongs to LPR, we say Xn converges to X if same definitions. For every epsilon positive, there exists an n epsilon such that n greater than or equal to n epsilon now implies summation j equal to 1 to infinity mod xn j minus xj to the power of p to the power of 1 over p is less than epsilon. This is rho xn x. Okay, I have written that rho p xn x in detail. Except the fact that last time we had finite number of terms, now we have infinite number of terms. There are so much data that's available. All the data has to be compiled. Okay. We will proceed in the same way. Like look at the columns. Okay. So for each k, look at xn k n equal to 1, 2, etc. The sequence of kth coordinates. Okay. The sequence of the kth. Same argument as before, no problem. We have xnk minus xk to the power of p to the power of 1 over p is less than or equal to xnk minus xk to the power of p to the power of 1 over p. There are more terms there and so on. So same estimate like last time. and we know that this can be made less than epsilon for n greater than or equal to n epsilon. So what does that say? That says xkn belongs to R is a Cauchy sequence of, not even that, even more, xn k tends to xk in R. That is all it says. Xnk minus xk can be made small, so xnk converges to xk. So therefore, what we have is convergence in LP means coordinate wise convergence. So there just the same conclusion as before. So therefore, convergence in LPR implies coordinate wise convergence. But however, now the reverse is going to be messy. It is not going to be true. Because previously we said if each component can be controlled, then since there are only finite number of them, the total sum can also be controlled. But however, now I have an infinite number of components. Each term may be small, but infinite number of small terms added could become very large. So therefore, there is a chance that this may fail, and it does fail. Okay. However, the converse now is not necessarily true. That is, we may have coordinate wise convergence without having LP or convergence. We look at an example. For example, let me write on this side, so that I will write it as a matrix only, so that you see it clearly. Let us take the first element. It must be a sequence, it must belong to LPR. Its first component is 0 or 1 and all others are 0. Obviously, sum of the components to the power of p is finite. We need a mod xj to the power of p to be finite. Then only it will be in LPR. So obviously, this is the only one component, 1 to the power of p. In fact, it is mod xj to the power of sub 1. Then I look at 1, 1, then 0, 0, 0. Again, no problem. There are only number of components, the sum of the pth power will be finite. I do this, the nth vector will have the first n components as 1 and then 0, 0, 0. Right? That is my sequence, and all of them are in LPR. All of them are in LPR. Now look at the coordinate wise convergence. What happens to the first coordinates? It starts with 1, 1, 1, 1, 1, 1, 1, 1. Obviously it converges to 1. So the first coordinates converge to 1. What happens to the second coordinates? 0, then 1, 1, 1, 1, 1. So it again converges to 1. Third coordinate converges to 1. The nth coordinate, kth coordinates, nth coordinate is first is 0, then 1, 1, 1, 1, 1, 1, 1. So that also converges to 1. So what is the conclusion? All the coordinates converge to the 1. So we have coordinate wise convergence. However, that vector you got is not even in LP, because the sum of the peak powers is going to be infinite, but Xn does not converge to 111 in LP, or because this X does not even belong to, because if at all it converged by this, we must have coordinate wise convergence, and coordinate wise convergence says that this is the only possibility. So there cannot be any other vector which will do both coordinate wise as well as this. So this is the only possible limit. Because of this convergence, if it was there will be coordinate convergence, and coordinate convergence means only possibility is this, and therefore there is no chance of having convergence in LPR. So therefore in this case, whereas convergence in the space implies coordinate wise convergence, coordinate wise convergence no longer implies convergence in the metric. These two are now two different concepts. Okay. So what this says is, individually everybody may be nice, but when they all gang up, that's what happens in most of the time. When they all gang up, they are bad. Okay. So cooperative things sometimes may be bad, sometimes may be good. So individually they are all good, they are all nicely converging. When they all gang up and look at the consolidated thing, it's very bad. Okay, they don't converge. Yeah. Again? Yes. Yes. Tell me, you only tell me. Suppose, let us, okay, suppose this converges to 1 and this converges to 1 by 2 to the power of 1 over p. Okay. The third one converges to 1 over 3 to the power of 1 over p. Okay. Now what will be the sum? Xj to the power of p. 1 plus half plus 1/3 plus 1/4, and what happens to that series? That still diverges. So less than 1 is not enough. Finally it must add up to the p power to a finite quantity. Okay. So just being smaller than 1 is not enough. Just sufficiently small enough as keep on reducing very fast, not just at the rate of 1 over n, but a little bit better as we go further and further. Okay. So therefore, remember last time when we were dealing with finite vectors, we had convergence in metric is the same as coordinate wise convergence, and therefore our completeness proof was easy. We are given Cauchy sequence, we didn't know who the limit is, we went and looked at coordinate wise, we got an educated guess for the limit and we really proved him. But now if we got coordinate wise limit, that may not be a good guess. We don't even know whether that fellow is in the space or you have gone out, and that is your original problem, whether you are going to stay in the space when you take limits, and that is what the problem is, to decide whether it is complete or not. So completeness proof here, if at all it is complete, the completeness proof is not going to be straightforward. It is going to be a little bit harder. So therefore, what we should do is, we again make an educated guess as before through coordinate wise convergence, and we show that such a situation will not arise. The fellow we got at the end, coordinate wise limit, that new vector that we form is still in LP, and that is not enough, and then show that the original sequence converges to this new fellow you found in the metric. All these we have to show. So therefore, let me just outline what completeness here means. So therefore, again we make this statement analogously. Okay, analogously. So conclusion, in LPR we have convergence in LPR implies coordinate wise, that is all still there, coordinate wise convergence, but coordinate wise convergence does not imply convergence in LPR. This is what our conclusion of this discussion is. Okay. So from this, analogously, Cauchy sequence in LPR means coordinate wise Cauchy, but coordinate wise Cauchy cannot imply Cauchy in LPR. Previously we had both, and that is what helped us for a quick proof of the completeness of the space. But now we are going to have a little bit more extra effort to get this. So the question is LPR complete? See, these are the most standard spaces. If you are looking at the modern world of digitization, you are going to take any signal, any information, and then digitize it as a sequence of numbers eventually. So therefore, for this sequence of numbers, you want to attach some weight, some kind of a notion of a length, and the notion of error between two such fellows while you are doing approximation and all. And the errors that we will be using will be the P matrix. Okay. So these are very standard spaces when you are doing all this digitized analysis. And among these, the L2R is the most interesting one. Okay. The somehow connection with the energy, and therefore it is important. Okay. Again, what is the fundamental idea therefore? That, yeah. Which, yeah, in that example, all I wanted to show was I may have coordinate convergence, but I may not have convergence in the space. That's all. Yeah, it's certainly not a Cauchy sequence. Certainly not a Cauchy sequence, but I have coordinate wise convergence. That is because coordinate wise convergence does not imply, this is exactly what I got there. Coordinate wise convergence need not imply it is a Cauchy sequence. Good. That's a correct observation. Okay. So now, in order to show that it is complete, what are the things that we have to show? We have to show that for every Cauchy sequence Xn in LPR, there exists an X in LPR such that Xn converges to X in LPR. Everything must happen in that space. For every Cauchy sequence, there is a limit in that space, then only it is complete. So therefore, this is our aim. If we want to show that, we must take a Cauchy sequence. I will somehow concoct an X from that. That X must be in that space, and the X must be such that this converges to X in the LPR matrix. Okay. So, the idea, let me first write. We are given Cauchy and therefore coordinate wise Cauchy, and therefore the columns are going to converge. There is no problem. Only thing is that column limit that we got, we want to make sure that it does not end up with such trouble. Okay. So, the idea is the step 1, Cauchy in LPR implies coordinate wise Cauchy. That is this. Cauchy in LPR means coordinate wise Cauchy. Therefore, each column is a Cauchy sequence of real numbers. Same thing we did last time. And because it is a Cauchy sequence of real numbers, it must converge. Okay. So, that implies for each k, xn k is a Cauchy sequence of real numbers. And therefore, there exists an xk in R such that xnk tends to xk in R. In the finite case, we put x equal to x1, x2, xn. There is no problem, there are only a finite number of them. Now we are going to put these infinite fellows and call it x. Okay, let x equal to x1, x2, xk, etc. Then 1, this is step 2. Make sure that this x is in LPR. Because first, otherwise, you caught a fellow as a murderer and he does not even belong, a citizen of this country. He was not even here any time. You go and caught that fellow as the murderer. So that's somebody from outside you had got. So you must make sure that this fellow is the man here. For this, what should we say? Somebody is in LPR if sum of the components to the power of p to the power of 1 over p is finite. So that is make sure that summation j equal to 1 to infinity mod xj to the power of p is finite. That is what you have to make sure. Now, having made sure, then you have a possible murderer. Then you have to establish that he is the step 3. Make sure that xn converges to x in LPR. Now, if I did not have step 2, this step does not even make sense. When x is not even in LPR, what do you mean by saying xn converges to x in LPR? He is somebody outside. So, in order to write this step, I want to make sure. So, for this, that is, make sure that rho xn, that is for every epsilon positive, there exists n epsilon such that n greater than or equal to n epsilon implies rho xn x is less than epsilon. Right? Then we have done a decent job. We are given the Cauchy sequence. We first guessed the limit and we said that that limit is a reasonably good guess because he is in the space, and then we established he is indeed the right guess, showing that he is indeed the limit. So, this says the first step is to make a guess. The second step is to show that the guess is a reasonable guess, and then the step 3 is your guess is right. These are the 3 steps involved in the proof. Okay, right. So now I will indicate what is the first step is already over. Okay. Now you see the step 2. You want to make sure this is finite, right? In order to make sure this is finite, this is a sum of non-negative terms. Therefore, that's an infinite series. The infinite series is the limit of the partial sums, and because non-negative term, the partial sums are slowly increasing. So you want to put a cap on it to make sure that it converges. So all you have to do is to show that j equal to 1 to n mod xj to the power of p is finite, is dominated by one constant for all n. Okay. To prove, let me call this as star. To prove star, it is enough to show that there exists a real number k greater than 0 such that summation j equal to 1 to n mod xj to the power of p is less than or equal to k for every n. So the partial sums are all bound to k. It cannot fly off to infinity. So I am blocking them going away to, however many terms you take, they are staying below k only, and I am not allowing to go to infinity, and therefore the sum must be finite. So that's the idea, right? And in step 3, again I will come back to step 2. The same idea I will use. What does this mean? I want to show that all that for every epsilon greater than etc., this one can be written as summation j equal to 1 to infinity mod x and j minus xj to the power of p is less than epsilon. Now again, it is enough if I show this is less than some epsilon by 2 for every n. So the epsilon by 2 is the caps. At most they go and bang around epsilon by 2, so the barrier is below epsilon. The final barrier will be below epsilon, so that limit n tending to infinity summation j equal to 1 to n, this whole thing to the power of 1 over p, I should put to the power of 1 over p, this thing is less than or equal to epsilon by 2, which is less than epsilon, and we are done. Okay. So therefore basically we are connecting the problem to finite estimates instead of infinite estimates. So basically the proof boils down to getting these two facts. I will call this as star prime, and this is double star, and this is a double star prime. So to get star I have to get double star prime, to get double star I have to get double star prime. Is that clear? Any questions about that? So that's all the proof is. Okay. Make a guess, show it's a reasonable guess, and show it is indeed the correct answer. And then to show that it's a reasonable guess, you want to make sure that that fellow is in. If that fellow wants to be in the space, this sum must be finite. This sum will be finite if the partial sums are bounded. So that's what you have to show. The partial sums are bounded. Secondly, you want to show it converges. If you want to converge, this must be small. This will be small if the finite sum is dominated by something smaller for all n, so that it will never cross and reach that fellow, and that's what it is. So therefore, the whole thing boils down to somehow controlling the head rather than the tail. Okay. So now let's look at how we will achieve it. 5 minutes I will just indicate these proofs. So far the only place we have used the data What is the data? Xn is a Cauchy sequence. That is the data given. We are trying to find out all these other fellows. So the given data is Xn is a Cauchy sequence. That data we are used in this step. Okay. Now we will write that data again carefully, and from that we will get everything. I will just indicate the proof. So Xn Cauchy, you should go through this proof several times, so that you know the essence of many of the proofs are in these arguments. Okay, essence, most of the proofs there will be this sort of arguments. Xn is Cauchy. What does that mean? For every epsilon greater than 0, there exists an n epsilon such that n and m greater than or equal to n epsilon implies rho Xn Xm is less than epsilon. This is the given data. Let me call it as A. That is the given data. From that everything has to be obtained. Step 1 is obtained from that, because Cauchy in LP means coordinate wise Cauchy, and that gave us convergence, etc. Now I am going to use the same data to get all these other things also. Okay. We can do it for any epsilon. For every epsilon, there is a corresponding stage beyond which this error is smaller. So let us take epsilon equal to some quantity 1 for convenience. So what does that mean? There exists an n1 corresponding to that, such that and n and m greater than or equal to n1 implies rho Xn Xm is less than 1, right? I can make the error to be smaller than 1. I can make the error to be smaller than any positive number. In particular, I can make the error to be less than 1. Now, therefore, there exists n1 such that, let me write this first. Is this true? See, this is true for any n and m which are greater than n1. In particular, if I take m to be n1 and n to be something greater than n1, it will still be true. So therefore, rho of xm minus xn, rho of xn xn1 is less than 1. So in other words, there is a fixed vector called xn1, and then you move around the other fellows greater than the other side, the error will be always less than 1. Okay. What does that mean? All rho p, okay? That is summation j equal to 1 to infinity mod xn minus xn1, I think this is all j to the power of p to the power of 1 over p is less than 1. That is all the expansion is. Okay? See, now what I am going to do? What did I want? That I am going to get star prime. To get star prime, what do I want? Summation xj to the power of p. So summation j equal to 1 to n mod xj to the power of p. I will calculate to the power of 1 over p. If that finite, the p power is also finite. Okay. So now I can write this as I just added xj and 1 subtracted xj and 1, because I am able to control that difference somehow. So therefore I am bringing it that difference, xj minus xj. Right. Now what do you apply in whenever you have such a thing? Minkowski, right? So the Minkowski says this is less than or equal to right mod alpha j plus beta j to the power of p is less than or equal to mod alpha j to the power of p to the power of 1 of p plus mod beta j to the power of 1 of p. So I have just applied Minkowski. So that's why these inequalities are bread and butter issues. Okay, what is my aim? My aim is to show that this fellow can be dominated by one constant. So I will show that this is dominated by one constant and this is dominated by one constant. So totally they are dominated by one single constant. How do I get this? Let us look at only that part. Okay. From here I get summation j equal to 1 to n is less than or equal to the whole sum. If I take only n terms, that will be smaller than taking all the terms. Even if I take all the terms, it is less than 1. So if I take only n term, that will still be less than 1. And this is true for what? For any n greater than or equal to n. So there is only a finite sum now. I can take it as n as what should I say? There is a big mess here. I will call this as these two n's are different. This is the summation index. So what I will do is I will put a capital N here. Okay. So that I am sorry, everywhere the capital N I will put, so that there is no confusion between the n's. So I will put a capital N, capital N, capital N, and capital N. So the whole sum is less than 1. So only if I take n terms, capital N terms is less than 1, and this is true for all n greater than or equal to n. Now suppose I will say let little n go to infinity. What happens? The limit of a sum is the sum of the limits if I have only finite number of terms. Now I have only a finite number of terms. I will let it go to infinity. This will not. Coordinate wise convergence will say that will go to xj. So let n go to infinity. It implies summation j equal to 1 to n mod xjn minus mod xjn1 to the power of p to the power of 1 over p. In the limit at most it can become equal to 1. So therefore, should I say xj? Because the limit. Therefore, where was this? This term is at most less than or equal to 1. That's all. It cannot be less than 1. So that is dominated by constant. What about the other fellow? For the other fellow, he is a fixed vector. He is certainly less than or equal to right? Instead of taking a finite sum, take the full sum, and that full sum is finite. Why? Because xn1 is in LP, that is one particular vector, one particular row, and that is in LP, and the row sum pth power is finite because it is in LP, and therefore it is one fixed row sum. So that is the constant. I will call it as the n1th row sum, and therefore together they are all dominated by one constant kn1 plus 1, and that proves this part. Okay, the idea is the idea that's important. Okay, so you want to prove the infinite sum is finite. See, normally what I would have done is, this is finite. I would have liked to put n tend to infinity and conclude xj to the power of p is finite. But the limit of a sum is not equal to the sum of the limit if you have infinite number of sums. So therefore I labored to bring it down to the taking the limit of a finite sum and then push the limit inside. Okay. and that is the reason why all this n1 etc. had to be brought out. And analogously the same thing can be brought. This sum, this is true, we have this, right? One over p is less than epsilon. You can make it epsilon by 2 or epsilon by 100, whatever you want. Whatever small number you want to make, the error can be made small. So now I would have liked to push m go to, suppose I push n go to infinity, then I got xj minus xj to the power of p finite. But then I can't push n go to infinity in this, okay, because there are infinite number of sums. So again I will bring it back to the finite sum situation and show that the error can be controlled. So a similar idea, okay, I will probably establish a similar idea as before, gives double stop. So therefore the proof of the completeness in the infinite component case is not straightforward. In the previous case we had coordinate wise and LP convergence completely merging with each other. In this case convergence in LP gave only coordinate wise convergence, and then I had to work hard to show that the limit I got is in LP and is indeed the limit of the sequence. So, well, you have to pay a price if you are passing a second standard exam is much difficult than 8th standard, then infinite standard is going to be much more difficult. Okay. So therefore, the infinite dimensional spaces, certain things may not work as well as you like in the than as well as they did in the finite dimensional case. First of all, I had to put a restriction that sum is finite to be included in the space, and even when I put that inclusion, coordinate wise could not imply LP convergence. So the Cauchy-ness to convergence, I had to work hard to get the completeness. So, but the fact of the matter is, despite all this, we could arrive at the fact that LPR is complete. And similarly, when p equal to infinity, the math is taken through. So we have LPN R, where p can be 1 to infinity, LPR from p equal to 1 to infinity. And since in all these cases we are using only modulus in our estimates, we could as well have put complex numbers. So it is also LPC and LPNC. So the main conclusion of today's lecture is that LPNR, LPNC, LPR, LPC are all complete metric spaces. Are all complete metric spaces. Okay, so we have now with us a large number of complete metric spaces. The n component vectors and the infinite component vectors, the p norms. Remember that when we were in the finite number of components, convergence in all the p metrics was equivalent to coordinate wise convergence. We do not have that luxury when we go to infinite component vectors, because first of all these convergences are not at all equivalent. The spaces are all different. Okay. For to be in LP, it has to be the pth power should be finite. To be in another P1, the P1th power should be finite. And also coordinate convergence does not imply LP convergence. Therefore, these are not equivalent. So we get different notions of convergence now. Whereas in finite dimensional spaces, that vector spaces we had, all these rho p metric gave the same notion of convergence. The limit was the same, everything would go the same. However, in infinite dimensional cases, we have not different notions of convergence. Even in LP, fix a P and look at only LP, There you have now two notions of convergence. One is coordinate wise convergence, one is consolidated convergence. That consolidated implies coordinate, but coordinate does not imply consolidate. So there are now different notions of convergence. All these are examples of discrete things. The components are all discrete, x1, x2, x3 like that. Suppose we have a continuum of components. So instead of xj, I will have x of t. So then we will move to function spaces. So instead of now vectors with discrete components, we now take vectors with a continuum of components, which boils down to functions defined on some interval of t. Now what about those spaces? That is what we will discuss in the next class.